Hi, this is your astronomer who moved from Helsinki to Rome in pursuit of a postdoc, and I am excited because today I am recording my first video on this, which I hope to become a series of videos on galaxy topic, galaxy science, galaxy survey science, technical videos. So because it's my first videos, I already took maybe 5 takes and they all failed. Hopefully this one works out. First of all, I am celebrating because it is in celebration of my career advancement to this stage in research, postdoc stage, and then I would like to express gratitude to God to give me the resources of time and equipment to be able to do this, and also my husband for providing this kind of arm to do this kind of writing video, and to my dad who provided these square papers back from his printing days ages ago, but I still have this and I'm using it for this video recording, so thanks, Dad. Yeah, and thank you for my husband because it's a Sunday and he's babysitting the kids so that I have time to record, and it's taking a long time because I keep failing. So hopefully this is the last one and there are no error messages and sudden stops. I had my phone, basically the storage would fail for some reason, and I tried everything I could think of, to even reinstalling and deleting everything on YouTube. So now I'm recording this with the native video app, and hopefully there's enough storage for me to do about 10-minute video, I think. But I will redraw what is the concept. The concept is flat sky approximation. So I'm using today just your regular arsenal of different kind of pencils. I have some rulers at my disposal, these kind of rulers, we'll see what we need, and some of colored pencils in case we need. Actually, let me bring some more pencils, I mean pens, maybe these ones. All right. Okay, I think I'm set up. So I want to talk today about flat sky approximation. What's my audience is a whole wide world, so let me know if you have any questions. I'll try to answer them as I have time, but hopefully this video inspires and reaches people all over the world and supports your interest if you want to do science. I always label with a date anything I write on paper. Flat sky approximation. Okay, before we go to flat sky approximation, let's discuss the celestial globe. All right, I'm gonna be using a small ruler just to help myself here. I found on my to draw some helper line on this paper is from a notebook. I tore it out, it tears out easily, and on the back of the notebook that I found some of your handwriting, so it was nice. My dad's handwriting is quite hard to understand. My mom's handwriting is amazingly nice and beautiful and easy to read. Mine is so I hope you can read what I write. But basically these are helper lines at 90 degrees. We'll do a circle and then another one, a flatter one. So if I imagine that I am on a surface of the earth, it's not to scale, so let's say this is my earth, if I am an observer standing somewhere on the surface of the scale, oh, can you see this? It is observer. It's like the reference point where everything begins, like the 0, 0. We can even draw a person with a telescope. So let's give it some hair. I have long hair. I can imagine that there is a globe all around me, that the Earth and myself were embedded in another globe, which is the celestial globe. Celestial globe. So all the way on underneath, right underneath my feet is the celestial South Pole. And also at the top of my head is another important point, the celestial North Pole. And this, maybe we'll use shade. And this flat surface that is somehow perpendicular to the Earth's radius that starts from the center of the Earth and ends with me. This flat surface, 2D surface, is a celestial equator surface. It's a surface, so it doesn't end here, right? It goes beyond. But we think that the globe is contained, so here are its containment kind of guidelines. And now we can, like a position of, let's say, Italy or Rome can be described by 2 coordinates on the globe, latitude and longitude, we can imagine that all these luminaries we observe at night and the sun during the day, or luminaries during the day, doesn't matter what time. Let's say it's the Betelgeuse. We'll do in pretty red color. That it can be described also by 2 coordinates. If I have one angle is the declination angle. So it goes from the celestial equator to that star. Maybe the star even will be gold, yellow. So this angle is delta, is a declination. So one angle is delta, declination. Can you see it? Yes. All right, golden it with blue. Delta is declination. Or DECL, abbreviated as DCL. At the equator, delta is 0 degrees. At the celestial South Pole is negative 90 degrees, and at the North Pole, celestial North Pole, delta is positive 90 degrees. So delta goes, the declination ranges from minus 90 degrees, bottom of our feet, beneath our feet, to top of our head, which is positive 90 degrees. In this usual interpretation, sometimes it goes 0 to 180, but we'll stick with this. Then there is another coordinate for the celestial coordinates, because we need another one. We imagine, let's use purple, a reference line, some reference line, reference curve, pole to pole. and where it crosses the celestial equator line, we call it a reference point, and it is 0 degrees. We'll call that angle alpha. And from that reference point, the angle all the way to our point of described by the delta and described by the guided by the star to that point in the equator is our second coordinate, alpha. Alpha and delta of star. So, and it's right ascension. Can you see that far? Yes, you can. Right ascension. Okay, can I spell it? Ascension, I believe. Okay, see us here. All right, these are our two coordinates. So they are angles, so they have curvature. They have curvature. Okay, and this beautiful right ascension coordinate goes from 0 to 360 degrees. So it goes full circle like this. So you can imagine that when it crosses in the back of you on the other side, the equator, there alpha is 180 degrees. Then it goes another 90 degrees. It will be 270 degrees, and then it goes back full circle to its reference point to 360 degrees, because a circle is 360 degrees. So this is where this comes from. But of course, sometimes we have, just as in geography, another way of describing the values of this coordinate in terms of hours, minutes, and seconds. So it can be expressed that way as well. Okay. So this is our celestial globe, and it is important because we need to account for this curvature if we have a galaxy survey that is covering a significant portion of the sky. Anytime, actually, ideally, you would have this curvature accounted for, but especially if you have a full sky galaxy survey, for example, SDSS or Pan-STARRS. Wasn't there 2 R's, I believe? These kind of surveys always need to take into account the curvature of this coordinate system. Okay. However, if you have a small galaxy survey, if it is small patch of the sky, and especially if it is equatorial, you can use a flat sky approximation and ignore the curvature effects. What do I mean? Because if you are in polar regions, see, the lines are combining, meeting each other here, things are shrinking, so it's a problem. When you go to polar regions, it's a problem. You cannot, you have to either describe what happens if you are doing a flat sky approximation so that people know, or just not use it. But if you are kind of in the green zone around the equatorial regions, then it is lines are more parallel to each other, so the flat sky approximation works better, and the curvature effects are small. So if you have a region that avoids the polar regions, and you have just, I don't know, 1 degree patch on each side of sky, then it is small enough that it is kind of like a square. So you can use concept of the flat sky, which is basically, it's like a sheet. The sky is a sheet. It's a surface, 2D surface, and you can use your regular geometry, orthogonal, right angle geometry, to describe the position. Let's say this is alpha, right ascension and declination. This is your observer, this is your star. The position can be just described by these coordinates, and the relative positions also. Let's say there is another green star here. Can be described by right angle in this case, or some regular geometry, orthogonal geometry, formulas and relationships. So it is much easier to calculate things. And this is your flat skies approximation, because you assume that sky is flat, there's no curvature, and lines are straight. Lines don't intersect when they, like this delta doesn't go and intersect with the next delta on this surface. They are parallel to each other, and the same thing for alpha, they don't intersect. So this is your flat sky approximation, and you can actually take in your small patch of the sky, you can take, and see what is the distribution of your, that's what first thing I would do, to map your galaxies or catalog of stars and see what is the distribution. Yeah, so you can generate this kind of a map, and this we will do in the next video, and I will show you a Python program that does that, and I will show you what tools I use, because if I was calculating like distance from here to here, then I would have to make sure I take into account the curvature and follow what it's called the great circle relationships. But here I don't have to do that. If there are two objects, their distance can be calculated based on their coordinates using a regular orthogonal geometry or right angle geometry, XY geometries that you have learned in the beginning of your school. All right, I will end here. Let's see if I can shift. Thank you for staying with me. God bless you.